Hello everybody and welcome to the last lecture of our lecture series Datasets and Preprocessing. In this notebook you will learn how to handle three-dimensional medical image data and how to preprocess those datasets. To demonstrate this, we will use a brain MRI scan distributed by the IXI dataset. We already provide this file in the corresponding directory. In addition, as usually, we include the link to the dataset as well as the corresponding license in the Jupyter notebook. To address this issue, we use the following libraries. As all files in the IXI dataset are nifties, we will use nibabel to load them. Of course, we can use matplotlib to visualize some slices and numpy to perform the matrix vector calculations. Additionally, we use the magic command matplotlib notebook, which increases the overall usability of our plots. Alright, let's get started. After importing the necessary libraries, we load the T1 weighted brain MRI scan and extract the volume by using nibabel. Let us store the nifty in a variable called brain MRI and then call nib.load, where we pass the path to the file. We store the actual volume in a separate variable called brain MRI data. As you already know, to extract the actual volume we call brain MRI.get_f_data. After loading the nifty and corresponding volume, we can inspect its shape and affine matrix. As we need the affine matrix later to transform coordinates between the physical and the voxel system, we store the affine matrix in a variable called affine. You can simply extract the affine matrix by accessing the affine attribute of the nifty file. And we perform the same operation for the shape. Now we can take a look at those variables. At first the affine matrix, and as you can see, it corresponds to a 4x4 matrix, where the last row, corresponding of 3 zeros and a 1, and the last column, describing the offset, is simply appended for convenience to directly incorporate the translation. The 3x3 submatrix defines the scaling, rotation and shearing parameters. The shape of our volume is 256 by 256 by 150. We can access the size of a voxel in the volume by using the header.get_zooms function provided by nibabel. It returns the size of a voxel in all directions in millimeter. In our case, we at first access the header attribute of our brain MRI, followed by the call to the get_zooms function. This tells us that each voxel in the scan covers an area of 0.9375 mm in the first direction, 0.9375 mm in the second direction, and 1.2 mm in the third direction or axis. Of course, you can slice through the volume in all three orientations: axial, coronal and sagittal. Note, and this is extremely important, depending on the orientation of the scan, the indices change. Sometimes the first axis has axial orientation, sometimes coronal and sometimes sagittal. Again, this shows why you should check your orientations as a pre-processing step. You can find out the orientation by using nibabel.affine or AFF to ax codes, where you simply pass the affine matrix. This always returns a tuple with 3 letters. Those letters always indicate the end of the corresponding body axis. Please remember the plot from the medical basics section, which shows the different body axes. In this case, the letter P shows us that the first axis moves from anterior to posterior, that is, from front to back. The second axis, indicated by the S, moves from inferior to superior, that is from bottom to top, and the third axis moves from left to right. Now that this is known, please think briefly about which axis corresponds to the axial view, which corresponds to the coronal view, and which to the sagittal view. As the first axis moves from front to back, it corresponds to the coronal view. The second one, which moves from bottom to top, shows the axial view, and the last one from left to right, the sagittal view. Now it's a good idea to slice through all three orientations and visualize some slices to get a feeling for it. At first we move along the first axis. This moves through the face to the back of the head. Let us visualize two slices by using plt.subplots. We want to use one row and two columns. The first plot should show an area in the front of the head and the second one in the middle of it. We can now access the first and second axis object, call.imshow, and select the slices we want to visualize of brain MRI data. A slice which contains parts in the front of the head might be slice number 40. To get the remaining pixels along the other two dimensions, we use the colon operator. To visualize a central part of the brain, we can simply copy the above snippet and at first replace the axis index to 1 and the slice to maybe 120. Oops! Now we forgot to change the color map. Let's quickly fix this. Alright, but still something seems kind of strange. Why is the plot upside down? Please think about the orientation of this particular scan for a second and try to answer the question. Okay, the reason is that the second axis moves from the bottom to the top. This means that the first slice is somewhere in the neck or jaw area. To slice along the second axis, we can copy the above code snippet and change only the position of the slice variables. As an example, slice number 30 should roughly cover an area of the jaw or mouth, while slice number 200 should show the upper part of the brain. Let's have a look. And as expected, you can beautifully see some teeth in the left figure visualizing slice number 30 and the upper part of the brain in the right plot. Last but not least, we slice through the third axis, which moves from the right ear to the left ear. Again, we simply paste the code snippet from above and change the location of the slice variables. Let's simply try slice number 20 for the left plot and slice number 45 for the right one. And as you can see, we are moving through the head from the left to the right. Again, please take a moment and think about why the head is rotated. The reason is that the first axis of this scan moves from front to back. This corresponds to the y-axis in this figure. Therefore, the first slices contain parts of the face, whereas the last slices contain parts showing the back of the head. In the associated Jupyter notebook for this lecture, you can find instructions on how to adjust and change the orientation of the scan so that the plot is no longer rotated or upside down. However, these functions do not change the affine matrix and are therefore very dangerous to use. Please make sure that you only use them for the sake of visualization. Now it's time to take a look at the calculations we need to transform coordinates between the two coordinate systems. At first, we have to define our voxel coordinates which we want to transform into the physical world. To do so, we can create a NumPy array containing a list or a tuple with the coordinates. As an example, let's simply say we want to compute the coordinates of the offset 0, 0, 0. Additionally, for convenience, you add the 1. Now, let us define a variable called physical coords, which will take the result of the transformation. Now, as shown in the lecture, we compute the matrix multiplication between the affine matrix and our voxel coordinates. Note that the @ sign is a shortcut for matrix multiplication in NumPy. Let us now take a look at the physical coordinates. To verify that this result is correct, we can print the last column of our affine matrix. Perfect! We just transformed the voxel coordinates into the physical world. We can also skip the shortcut and compute the result by hand. To do so, we define a variable called voxel_coords_manual, which will again take a NumPy array containing the coordinates. Note that in this case we don't want to add the 1. Now let us define another variable called physical_coords_manual and then compute at first the matrix multiplication. To do so, we access the first 3 rows and the first 3 columns of the affine matrix and multiply this matrix with our voxel coordinates manual variable. Next, we simply add the offset to this matrix by accessing the first 3 rows of the last column. Now we simply print the result and verify that it is identical to the one above. Perfect! As you can see, both ways work. However, the first one is much more convenient. Of course, we can also transform physical coordinates into the pixel or voxel ones. To do so, we simply need to compute the inverse of the affine matrix and multiply this inverse with the physical coordinates. As an example, let us convert our just computed physical coordinates into the voxel space. We can simply copy the list from above. We now use numpy.linalc.inf, where we pass our affine matrix and multiply this result with the physical coordinates. And as you can see, the result is basically 0. To clarify this, we can simply round the result. Perfect! Now we are able to transform coordinates from the physical space into the voxel space and from the voxel space into the physical one.